So go ahead and pull up the Chapter 12 worksheets. So we talked a little bit at the beginning of the quarter, I think, about spontaneous versus non-spontaneous processes. Spontaneous being processes that go on their own. So they just take place without adding any energy. So for example, in the first picture, when the rock is balanced on that tip, right, if the person lets go, it's going to fall by itself without any input of energy. It's going to fall maybe down the hill or maybe back to where the person is standing. But if it's up on the tip like that, it's going to fall spontaneously. In figure B, it requires initiation, like a spark for combustion reactions. And if we initiate it, if the person tips it up like figure A, then it's spontaneous. Once it's started, it will go spontaneously until it comes to rest somewhere. A non-spontaneous process is the opposite. It goes in the opposite direction. So it requires a constant input of energy to keep moving forward. So figure C would be the example of the non-spontaneous process. It's spontaneous in the reverse direction. So here we're just talking about things that will happen on their own versus things that require energy to push them along. And that's independent of how fast something happens. So we're going to talk a little bit about kinetics, how fast reactions go. So for example, here, figure A and B, these images are both oxidations. These are oxidation reactions. The explosion is fast. And once it starts, it's spontaneous. It combusts all the fuel that's available. In figure B, it is spontaneous. It will happen. Rusting will happen in the presence of air and water. And it's just really slow. So it takes a long time to build up all that rust. So let's take a couple minutes to think about these examples here at room temperature. And that's an important part of it. We want to make sure that we're talking about room temperature. So a drop of food coloring spreads in a glass of water. True or false? Is that spontaneous at room temperature? Yeah, that one is. Right? You put it in water and it'll spread out. And I think I have a little video posted, the gas video. It's like 3 minutes long. It's excellent video, worth watching. All right, methane burns in air. Is that spontaneous at room temperature? This will require a spark. Yeah. But once it gets that, yes, it'll go. Wait, what's happening here? Yeah, once it gets that, it will proceed forward. What about water freezing into ice? Is that spontaneous at room temperature? So liquid going to solid at about 25 degrees C. Yeah, that is not spontaneous. It's spontaneous in the other direction. So if you had ice cubes, they would spontaneously melt at room temperature. And then what about iron rusting, iron metal rust? Yes, that one is spontaneous at room temperature. All right, so let's talk about collision theory. In a chemical reaction, we're looking at reactants converting into products, and that can happen fast or slow. So when we talk about the rate of a chemical reaction, we're talking about how fast those products will develop. So we could start with something that has all reactants and produces a color change, for example. Maybe it forms a brown gas. We can measure how fast that brown gas is generated, and that would be the rate of the reaction. So studying all of this, how fast reactions go, is kinetics, chemical kinetics. Collisions are really important, and collisions have to have certain properties in order to move reactants toward products. So they have to have a collision that has enough energy that it can break the bonds that are supposed to break. So we're really looking, if you look at the reactant side and compare them to the product side, what has to happen there? We have to break some bonds and we have to form some bonds. And we have to break that N-N triple bond is super strong. So it has to be a strong collision. It has to have the right orientation in order for these bonds to break and a new molecule to form. So all of that has to happen in order for reactants to go to products. So the more often they collide, the more likely they are to have a collision that meets these criteria. So we can increase the collision frequency in a couple of ways. One way is to increase the concentration. So increase the number of molecules that are in a given space or volume. That's easy to think about, like we skipped the gas law chapter, but if we were all in the same room and I said, okay, get up, everybody walk around, then we would have time to move around each other, right? We might have some collisions, but not too many. Maybe there's desks in the way. If I said, okay, now everybody run, we're all moving really fast, then we're likely to have more collisions. If we increase the temperature, we're going to increase the speed of those molecules. That's going to cause them to find each other faster, and it's going to cause them to have more energy when they do collide. So they'll be moving faster. The energy of that collision will be greater because of the speed. Those are two ways we can increase the collision frequency. Which will have more collision, a sample of nitrogen molecules at 25 degrees or a sample of nitrogen molecules at 100 degrees C. Okay, so in order for a reaction to happen, the collisions have to have enough energy. They have to be able to break the existing bonds so that they can form the new bonds when they have that collision. So if they're moving too slowly and it doesn't pull the atoms apart, they stabilize each other, then they just have a collision that's elastic that bounces off. And there's a minimum energy required for a reaction called the activation energy. And that's like the barrier here, right? So if this is where we start from, this is the energy it takes. The energy barrier, EA. So it's kind of like a backboard, like trying to hit a ball over a tennis backboard. You have to hit it pretty hard to get it up and over. Slightly different analogy, but this is called the activation energy. The size of that barrier depends on a lot of things about the molecules, but it also tells us how fast the reaction can happen, right? So if you just have the net, you can hit the ball over it easily, but if you want to hit it up over the big backboard, you have to hit it a lot harder. It might take longer to get that done. When molecules collide and they have enough energy in that collision that they reach that energy, right? Because here's our energy axis. When they reach that amount of energy from the collision, then they can possibly react, right? They get up to this part. That's sometimes called the transition state or the activated complex, sometimes a lot of words for that. So if the collision allows them to get that high in energy, then maybe they can go back down to reactants, or maybe they can go forward to products. But if they don't even get that much energy, then there's not going to be a reaction. They just have collisions and bounce off each other. So it turns out the temperature and the concentration don't give us an effective measure or prediction for how fast reactions go. We have a huge contribution from the collision geometry. They have to collide in the right orientation. So in this picture, we're looking at breaking this bond and forming this bond. So we want to transfer that oxygen from the ozone over to the NO. If they collide in this direction, even if it has a lot of energy, it's not going to be a productive collision, right? So this one is going to be no reaction because it's just not there. If that oxygen comes off, it's just going to get right back on that ozone. So they have to have the right orientation in order for a reaction to move forward. And it's quite a limitation because in 3 dimensions, there's a lot of ways they can have collisions that aren't just right. Factors that influence the rate of reaction. Temperature increases the rate of reaction in 2 ways. It increases the collision frequency because they're moving faster, and it increases the energy of collision. So it's easier to reach that activation energy. So temperature is a very effective way to increase the reaction rate. We see about a doubling of the reaction rate for every 10 degrees increase in temperature. Temperature has a huge effect. All right, concentration, the more molecules are in there, the more crowded it is, the more collisions they're going to have. So if there are more collisions, more of them are likely to meet the criteria for reaction. That typically will increase the rate. That's what we're going to be looking at in the lab next week. We can also increase the speed of reaction with a catalyst. And a catalyst is like an escort that gives it a new pathway. It reduces the activation barrier by just giving it a totally different path. So it's like instead of climbing up and over a mountain, it takes you around the side. It's like a guide that says, hey, come on, let's go this way. We'll get you there faster. The important things about a catalyst are that they lower the activation barrier by finding a new path, and they are regenerated. So it just takes a tiny bit. So it gets used, and then at the end, it comes back off, and it can go help another molecule. So really small amounts. Vitamins are all catalysts. Okay, now I moved this diagram earlier, if you remember, into chapter 5 when we were talking about covalent bond formation, because I wanted to weave those energy diagrams in all quarter long. We started with that in chapter on heat and energy. And here again, we are looking at energy, and this is literally kilojoules per mole. These are values that we measure. It's not just some abstract energy amount. And here we have the internuclear distance. This is an energy diagram, and sometimes we have what's called a reaction coordinate on the x-axis. It's like the path of the reaction. It's a little bit abstract. So when we looked at energy diagrams with our heating cooling curve, we looked at that heating cooling curve as constant heat added. We added heat like on a Bunsen burner, so we were adding heat at a constant rate, so we could kind of think of it like time because we were adding that heat. But when we think about a reaction here, we're looking at those atoms way over here coming together. I think I talked a little bit about like a vibrational level where they're really close here and they're vibrating back and forth. So this is really just to remind us of all the ways that we see energy diagrams, and this is the kind of energy diagram we're talking about now. Sometimes these are called, they might be called a reaction profile or an energy diagram. So let's take a look at this reaction. This is that reaction we saw earlier, ozone plus the NO. And in the forward direction, and this could go both ways, we're going to talk about both ways here. In the forward direction, it has a relatively small activation barrier. Those reactants come together, they start out at the zero, we set the zero of energy there. They reach that activated complex, which is like partly breaking a bond and partly forming the new bond. It's kind of right in the middle. So nobody has the full octet, like none of those are super happy, they're at a higher energy. But then that central oxygen sort of decides, is it going to go back on the ozone or is it going to go on the nitrogen oxide, monoxide? If we think about going in the back direction though, if the products are going to go back this direction, that has a much higher barrier, has a bigger hill to climb. So it's going to be a lot slower. It's going to take more time for that to happen. This is a bunch of text, and it is based on the textbook, which I'm not a really big fan of some of the wording in there. It's just very wordy. So what do we need to get from this? The difference between the reactants and the products, the heat of the reaction, which is often given a delta H. So I think we talked about this, didn't we? With when we did energy before, we talked about the heat release, endothermic and exothermic. So we're bringing that back, endothermic and exothermic. And it's just a new way to cast it in terms of the bond strength. And so what I want to do is use this energy profile to identify the activation energy in the forward and reverse directions. have some discussion about the strength of the bonds, because remember when we did the heat and energy lab, we saw the energy in to break the bonds and the energy released when new bonds were formed, and that balance with, do you remember those with the little purple and orange arrows? So I want to answer these questions for this diagram. So let me write what they are. We have the forward activation energy, we have the energy of activation in the reverse direction, and then we want endo versus exo, reminder, and the stronger bonds. Okay, so using that diagram. Okay, we've got the activation energy in the forward direction. That's written right on there. That is 10.5 kilojoules per mole. What is the activation energy in the reverse direction? So we're going to look at, from this point here down to here. So we have minus 200, and then we also have that 10.5. So let's add them together, right? We want that total distance. Energy diagrams are pretty intuitive, so don't get too tangled up in it. How big is that barrier? That is 210.5 kilojoules per mole. Is it endothermic or exothermic? So I'm going to write that in blue. When we think about the energy in or the energy out, we're going to start with the reactants. And in order to go to the products, what happened to this amount of energy? This is going to be our delta H. Is it absorbed or released? Energy in or energy out? Delta H is basically the heat released. Do you remember that? Do you remember doing endo-exothermic and looking at the heat released? So it's basically like the energy of the reactants equals the energy of the products plus that delta H amount. So this is, the heat released. When we see that the energy is negative, right, the energy down here, lower energy, is that more or less stable? That represents an energy stabilization. So which has the stronger bonds, the reactants or the products? The products have stronger bonds. They are more stabilized by having those bonds, and they have a larger energy barrier to break those bonds, essentially. So all of this information is coming to us through the energy diagram. Then the last one that I think we're going to go over is enzymes, biological catalysts or enzymes. This is an example of a sugar. It's got two rings on it, the glucose and the fructose sugar. So they're highlighting this bond that gets broken in the reaction here. And it's too slow, even at body temperature, to happen in effective timeline for life to exist. So we require enzymes, in this case a sucrase, and we're just showing that big green blue blob. It's all atoms and molecules. We have amazing simulations now. These basically fit those rings. The molecule will come into a binding site or a receptor site that fits based on its intermolecular forces, its physical fit together. And once that molecule is in there, the enzyme has a conformational change. It senses that that molecule's in there and it rotates in a way that pulls those rings apart. So it basically grabs the sugar and pulls it apart and then releases it. It's pretty special. It's pretty cool. So that's how enzymes work. And we'll just take a look at our energy diagram again with with a catalyst and with no catalyst here. Go ahead and work through these. So write the chemical equation. They give the reactants and the products. include heat as a reactant or a product. Remember when we did that? So I'm starting to bring in a little bit of review of some of the stuff that we've done. Is energy absorbed or released? Is it a reactant or a product? Yes, we're seeing that the reactants are at a higher energy and they're going to a lower energy. So in order for those to be equal, all of this must have been released. All right, the difference between the reactants and the products is what? That is, and you can see it labeled on there, that's the delta H, that's the heat. It's enthalpy or heat at constant pressure. How does the activation energy with a catalyst compare to the activation energy without the catalyst? It's reduced. So with the catalyst, it's less than without the catalyst, and you see that here. So what about the heat of reaction? Does the catalyst change that? The catalyst has no effect on the energetics. It doesn't change the reactants or the products. It just helps them get there faster. So, equal to. So, now I want to get to the equilibrium activity. So, if you have your pennies, let's just take a minute to shift over to that. The worksheet basically has these big boxes. I made my own. And then it's got a little graph. We're going to start with 24 pennies on one side. If you don't have 24 pennies, you can start with your number, but then you have to do all your counting. So you're welcome to do it, to run it with whatever you have. And then we're going to have 0 on B. So we're just starting with reactants going to products. So this is the sheet to use to do your work. And then the assignment is in here. And so I posted some of it here. This is that transparency framework, so hopefully it's helpful for you. That's kind of like a cover page. I'm going to try and use this as a cover page for students who want to know why we're doing what we're doing and what are we really doing. So I want to do task 1. We're going to work together as a class. I'd like to, I think I want to do the questions in breakout rooms so you talk to each other. And then we're going to work through the equilibrium and concentration gizmo, and there's just a few things and a couple of things I added. We may not make it all the way through there. You can do all of those on your own if you like them. Task 1 is the simulation. This is in the forum, and if you don't have a printer, you didn't print that out, just make a paper. If you need a minute to go get your objects, go ahead and do that, and I'm going to set up my camera. Okay, does that look like what you have? We're going to start with time step 0, 24 here. And I'm going to write those rate constants, and you'll see how we use them in just a sec. So K forward is 1/2. K reverse is 1/3. So I'm going to start with 0 products. And our reaction here is A going to B. All right, I have made little stacks of 5. So you can see I have 5 pennies, and those are my little stacks, 4 of those, and then I have 5 individual pennies. And I do that so I can easily count. I can see how many I've got there. If you have something that is round, it's a little harder, but you might be able to group it. Okay, so we ready to get started? All right, now what we're going to do in our first time step is we're going to use these little boxes below just to set things aside so we can count. There's nothing in B, so nothing can react in the reverse direction. But we have 24 of A, and our rate constant is 1/2. So we're going to take 12 pennies and move them to B. So I'm going to take 2 stacks of 5. And normally I'll like set them here for a minute and then they'll go right here. So now we count. At time step 1, we have 12 and 12. So now we're going to take a moment to plan our next step. And we're going to take half of side A, so 6 pennies, 1 stack, and then 1 individual. That's how many are going to react forward. And now we have to take 1/3 of side B. 1/3 of side B is 4. All right, so I'm going to take these guys and I'm going to spread them out so I see them. Okay, and at that time increment, now time 2, they're going to switch places. So these are going to go over here, and these are going to go over here. Now let's write down what the concentrations are of A and B. We have 1, 2, 3, 4, 5. Okay, so that is 10, and that one is 14. All right, in step 3, we're going to move half of side A, so 5, are going to move over to B, and 1/3 of 14. Now, if there is a partial penny, of course, with molecules, we don't have partial molecules. So we have to round down. So 1/3 of 14, the best we can do is 12. So we'll just take 4 pennies, right? All right, then at time step 3, they change places. At time step 3, we have 9 on side A and 15 on side B. All right, let's do one more time step. So we're going to take half of 9, but we have to round down, so that's 4 pennies. So 4 of them are going to move, and 1/3 is 5 of these. And then on that time step 4, they switch sides. So we have 10 and 14 again. Okay, so that's the end of simulation 1. I'm going to just make a line there. The next thing I want to do is add those extra pennies. I'm going to add 8 pennies, and I'm going to add them to side A. So there's 5, 6, 7, 8. Part 2, I'll call that time step 5. We have 18 and 14. Okay, so let's proceed. So we need to take half of 18, that is 9. So here's 9. And 1/3 of 14, and that's 4 again. So then at time step 6, they're going to switch places. Okay, let's do it again. Half of 13 rounded down is 6. And then 1/3 of 19 rounded down is 6. So at time step 7, they're going to switch places. And now we'll recount. These are the questions for this simulation. And I just thought of a new one. Maybe I'll just write it down here on screen. Why is this process called dynamic equilibrium? So that might be worth discussing as well. What I'd like to do is set you into breakout rooms and have you go through these questions. Hopefully everybody will have the assignment. They can see where we talk about these, and you can talk about your data or share your screen. I'm thinking that might take the rest of the time. if you are able to go forward with having someone share this gizmo, I didn't put the whole assignment in here because the copy paste wasn't formatting very well. If you can have somebody share that and work through some of that, it's a simulation like what we did, but it has more data with it. It's not, by hand. And so you can do a little more in that, just visualizing and playing with the amounts and looking at how it all works out. So you can work on that on your own if you don't get to it together in a group. So if I asked you to draw an energy diagram, we're looking for basically a couple things. We want to think about where are the reactants and where are the products and how are they connected. We have a couple different amounts, right? We have this value here, and we have this value here, and we have this value here. I could draw another one. I could draw another one like this. And that would have a series of those same things, right? We want to know, what's that energy difference? The heat that's absorbed or released. What is that activation barrier in the forward direction? What is that activation barrier in the reverse direction? Okay, so we want to be able to tie these together with endo versus exothermic. We want to be able to identify which direction is faster. I was thinking about those K values. I was thinking about KF was 1/2 and K reverse was 1/3. So this reaction was faster in the forward rate, was faster than in the backward direction. And so we ended up with a pileup of products. Which one of these diagrams would match that? We're looking for a smaller activation barrier for a faster reaction. So that was basically all. Let's go ahead and label these. Oh, which one's endothermic? Let me give this a 1 right here and give this one a 2. Which one is endothermic? Yeah, number 2. It takes energy to get to products. So that means that number 1 is exothermic. And probably it's faster, right? This is a smaller barrier. Now there's other reasons that reactions might be faster or slower. Not every exothermic reaction is faster, but they're commonly seen together.